Today we're going to talk about the exercises from section 1.2 of the Apex Pre-Calculus textbook. This is going to be an overview of functions in general. We've talked some about functions in our developmental math videos, specifically the MTE5 and MTE9 video. Talked quite a bit about functions and function notation. I'm going to give a little bit more formal definition of what a function is when we start off. That's going to help us answer some of these questions. So a function in pre-calculus is seen as a mapping from the domain which is the set of all input values to the codomain which is the set of all possible outputs keyword there is possible and then inside the codomain is a smaller set here called the range, and the range is actually the set of all actual outputs, so that a element of the set D that we call the domain maps into the range, and we're going to call this rule that maps it f of x, so that this element in the range is called f of x1, or we're going to call that y1, so that there's an ordered pair of the mapping x1, y1. What makes a function special is two rules. Every element in the domain maps to an element in the range to every element in the domain maps to only one element in the range. So if I would list out all the possible input values, they all have to have an arrow coming from them in this mapping, but they can only have one arrow coming from them. So this is a rule that we can depend on. It's always going to do the same thing, that every time I input something, I'm going to get an output, and I'm always going to get the same output. That's what makes functions special. So this is the technical, rigorous definition. The reason that I use this rigorous definition is because it's not always something that I'm going to put on a graph like we did with MTE9, where we talked about passing the vertical line test. I could have this bubble graph where I have the names of the students in the class, and then over here I could have the seat numbers. So for instance, let's just say student 1, student 2, student 3, student 4, so on. This could be things over here. I want to make something specific here called a one-to-one function to show you what it is, where the whole codomain is the no, that's something different. So I'm gonna I'm going to map to the range here. There's a smaller set, the range. That may not be the set of, called the codomain, but this is going to be, this one matches with maybe their seat number, right? The seat number, seat 1, the student's going to sit in seat 2. This one is going to sit in seat 3. And this one is in seat 4, and so on. That there's a 1-to-1 correspondence, we call this. This is a 1-to-1 function. And 1-to-1 functions are special because I can go backwards and say, well, if I know the output, I can find the input through something called an inverse function. So inverse functions, things that are inversible would be that you can undo addition with subtraction, or you can undo subtraction with addition. You can undo multiplication with division, or you can undo division with multiplication. You can undo cubing with a cube root. You can undo a cube root with cubing. Notice I skipped over square and square root. We're going to talk about that in a second, about why that's not quite a 1-to-1 function, because it wouldn't pass what we call the horizontal line test. In fact, let's talk about that right now, that this type of function would have to pass a vertical and horizontal line test. So y equals x squared would pass the vertical line test, but it would not pass the horizontal line test. There would be the same y for 2 different x's, which would make it not 1-to-1. I think that's enough preliminary on this, and I'll be happy to talk to you more if you have questions about functions and mappings and 1-to-1 functions. There's another thing called entire functions, which is what I was about to say before, where the range is the entire codomain. Usually those are odd functions where one end goes to positive infinity and the other goes to negative infinity, so that every point on the y-axis is taken up by something on the function. Those are called entire functions, is one of the names for them. There's another fancier word when you get to discrete math later, but for right now, you're sometimes interested in, did the function take up all, was the range equal to the codomain, or was the range only part of the codomain? In an even function like a parabola, you're going to see that it's going to have a minimum or a maximum value, and it's not going to take up all of the codomain. The codomain would be this entire axis. Answers could be sitting anywhere on that axis, but it's only going to take up part of that axis. All right. Question number 1, what does it mean? What does f of t tell you about the function f? What does it not do? So we're going to have to look at this bubble here, that there's going to be input bubble t. There's going to be function f for every input t. There's only one output f of t over here. So it does not have 2 outputs, 2 different outputs for the same input t. T probably represents time as well. It doesn't specifically tell us that, but we use the variable t to stand for time very often in mathematics, when we want to let you know that its time is the variable there. True or false, if g of x is equal to x squared, then g of 2 is equal to g of -2. That's true, because this is what we call an even function. An even function is one in which f of x is equal to f of -x. We'll prove that here, that g of negative x is equal to negative x squared, and negative times a negative is a positive. And so we're going to get x squared back out. This was a positive number. That's going to be a positive number. We're going to get the same positive number. If we would stick in f of 2, we would get 4, which is the same as if we would stick in f of negative 2. So this is a true statement. Number 3, true or false. You can't combine functions using both composition and quotients of the same function. That's not true. I can write something like f of x plus g of x over f of x, or I could write f of g of x divided by f of x, or f of g of x divided by g of x. I can do that. There's just going to be a restriction here that g of x is not going to be allowed to be 0, or f of x is not allowed to be 0, or whatever, that we might have something that we normally would be able to add up here, but we're not going to be able to add that value when this is 0 because we can't divide by 0. So it might put a new restriction on the overall domain of my output, but it's not going to stop me from being able to do that. True or false, the combination g of f of x is the f of x is the input for g of x. That's true. The input is the inner function. So this is called a composition of functions. And this is f of x here is the input for g. None of these parentheses mean multiplication. They all mean to find f of, so if I did, for instance, g of f of 2, I'd have to find what the number f of 2 is, and then I'd have to plug that in to the function g once they gave me the rule for g. So we'll do some examples of that so that you see. It does not look like they're going to give you any problems where you read stuff off of a table. So no tables. So we'll just go ahead and we'll solve these like this. So number 5, 6, 7, and 8 are all based off of the same definitions, that f of x is equal to x to the third. Over here further. There we go. Now you can see it. F of x is equal to x to the third. G of x is equal to x plus 4. And h of x is going to be a trigonometric function, sine x. I'm doing exercises that include some trigonometry things in this textbook. You can ignore some of those things if you're in the pre-calculus without trigonometry. You might get to those in part 2 of your pre-calculus class, but this is a combined one pre-calculus that covers college algebra and trigonometry for pre-calculus. So we're going to talk about trigonometric functions in here. Hopefully you've seen some trigonometric functions in your high school geometry or high school trigonometry class. If you took trigonometry with geometry or with algebra 2, usually it goes with one of those two things. So anyways, number 5 says x cubed divided by sine of x. This is the function here is f of x, and the function there is h of x. So we could write this as f divided by h of x. Either of these answers would be acceptable. They want you to write it with f of x, g of x, and h of x, though, to use this in the middle. But this is another notation that some textbooks will use. 6 says sine of x plus 4. So that is h of x plus 4. They don't want you to actually expand that with trigonometry yet. That's not what they want you to do. They just want you to replace the function named sine with the function named h. That's all that they were looking for you to do in this problem. Now they want you to calculate or find what sine of x plus 4 is with the plus 4 on the outside. So 4 is no longer added to the input, it's added to the output. So this is h of x plus 4. And number 8 is going to say 2x to the third times x plus 4. So this is going to be 2 f of x times g of x. Now that 2 can just be sitting there out front. So another way that we can write it is 2 times fg of x. I didn't even multiplication to be included. 2 times f times g, or I can write a multiplication dot, though I don't usually like the multiplication dot because there's another function that's an open circle. So if we write 2 letters next to each other in algebra, it implies multiplication. I like putting no symbol between them for multiplication, but putting a closed dot is sometimes hard to see whether somebody puts a closed dot or an open circle, and those are 2 different operators with functions. We'll talk about the open circle operator is what we just talked about in number 4 up here. Let me go back to that and show you the open circle operator that'll be in some textbooks. So this that has all the parentheses here, another way that people will write that is g of f of x with an open circle where the inner function is after the open circle and the outer function is to the left of the open circle. So it's not looking like this is inside and outside, but it is. But this is one of the operators in math that you have to read right to left. You have to do f first, and then you have to do g. So watch out for that one. That's just called a composition of functions. And it's not addition, subtraction, multiplication, or division. It's letting f of x be the input into g of x. Starting with number 9, we're going to determine the input and the parameters, which those are basically the same thing. The input variable, the parameters, the type of function. Okay. So given f of x is equal to 2x squared, g of x is equal to x minus b, find 5f of 3a minus g of 4. Okay, so my input variable here is x in both cases. B is just sitting there. It's a number that's a constant. We're not going to worry about it. The parameters are the things that I'm passing to the functions here. So my parameters are going to be 3a and then 4 respectively. So I'm going to have to find what f of 3a is. And that's going to be 2 times 3a squared. It's going to be 2 times 9a squared is 18a squared. I'm also going to have to find out what g of 4 is. That's going to be 4 minus b. Notice each time that I'm replacing the x, the input value over here in parentheses with the parameter that's being passed to it. Now I didn't have f of 3a, I had 5 times f of 3a. So 5 times f of 3a is going to be 5 times 18a squared. And then I'm going to subtract g of 4. So that's going to be minus 4 minus b. 5f of 3a minus g of 4 is going to be equal to 5 times 18a squared minus 4 minus b, like that. So 5f of 3a minus g of 4 is going to be 5 times 18. It's going to give me 90 a squared. I'm going to distribute this negative. And there's no simplification that I can do anymore because there's no like terms left. I'd have to know what a and b were to be able to simplify that expression anymore. So I'm done. I've added all my like terms that are there. All right, number 13 says f of x is equal to x squared minus 3. G of x is equal to x minus b. We want to find f of y plus h minus 3 g of 5. Again, variables are x, parameters are y plus h and 5. They're the things that I'm sticking in. They want to give you some practice here with squaring a binomial. And this is going to be important when we do difference quotients. I'll write out what a difference quotient is for you at the end of the lesson because it's going to be something important for you to practice. And it doesn't look like we're doing any difference quotients specifically. Oh, yep, we are. We're going to do a difference quotient in the next one. So no, we won't because it's not the same function. Okay, so we'll talk about difference quotients before the end of the lesson. F of y plus h is going to be y plus h squared minus 3. This is y plus h times y plus h. There's going to be a pattern that you're going to be able to follow for a perfect square that we talked about in our MTE6 video, that you're going to see that it's going to be the first one squared plus 2 times the product of the middle ones plus the product of the last, because this outer and this inner are always going to be the same. So there's going to be 2 of them. So that's going to be my f of y plus h. Now we want 3 g of 5. Let's see if we can do this all at once. So 3 times 5 minus b is going to be 15 minus 3b. So now we want to subtract those 2 things. F of y plus h minus 3g of 5 is going to be y squared plus 2y h plus h squared minus 3 minus 15 minus 3b. There's going to be some like terms here in these constants that we're going to get to combine. So this is going to be y squared plus 2yh plus h squared minus 3 minus 15 plus 3b. There's no b's anywhere in the first one to combine. We're only interested in this negative 3 and this negative 15 are going to make a negative 18. Number 14 says f of x equals 5 minus x, and g of x is equal to negative x to the 4th plus p. So we want to find f of y plus h minus 3g of y. So 5 minus y plus h minus 3 times g of y. We're going to replace the x's with y's. This is going to be 5 minus y minus h plus 3y to the 4th minus 3p. Get my y terms together here, my h terms together, my p terms together, and my constants at the end. All right. Again, the variables were x, parameters were y plus h and y, and that's it. This next one is interesting because it's got a Greek letter for the variable theta. Theta usually implies that this is an angle that we're putting in, usually in radians. In fact, almost always in radians. So f of theta is going to be theta plus 3 over theta minus 2. G of theta is going to be theta squared plus 4. And they want us to find g of f of 3. I've got two options here. I'm going to show you that it gives me the same thing. The first thing that I'm going to do, though, is I'm going to do exactly what it says, and I'm going to find f of 3. I'm going to show you that this is going to be equal to the same thing as g of f of 3 in a second. I told you we could write it that way too, and that I can find what this composition function is and then stick 3 into it. I'm going to do what it says first. F of 3 is going to be 3 plus 3 over 3 minus 2 is 6 over 1 is 6. Now I'm going to have to take that and replace it here, but that's g of 6. So g of 6 is going to be 6 squared plus 4 is 36 plus 4 is 40. All right, now I'm going to start over and I'm going to show you that it works the same way. If I go ahead and say, I want to find g of f of theta. Let's start off with that. So I'm going to plug f into g. So g of theta plus 3 over theta minus 2 is theta plus 3 over theta minus 2 squared plus 4. I'm just going to leave it like that. There's no reason to simplify that right now. And then I'm going to plug in 3 so that this is 3 plus 3 over 3 minus 2 squared plus 4. And it's going to come out the same way. That's still going to be 6 over 1 is going to be 6. Is going to be 36 plus 4 is going to be 40. Sometimes by doing this composition, the function will actually simplify itself a little bit and make it more obvious what the answer will be. Sometimes it won't. So but there will be parts sometimes of these functions that will undo one another and will make your answer much easier, especially if they're inverse functions. Because inverse functions are going to have a special rule that when we compose them, if we're going to talk more about inverse functions later, but if f of x and g of x are what we call inverses, then by definition, f of g of x is going to give me x, and g of f of x is going to give me x. Both ways. That's why I was telling you that square roots and squares are not going to undo one another, because while the square root of x squared is x, the square root of x squared is actually equal to the absolute value of x. This is always going to return a positive value even when x is a negative value, and that doesn't give me back my original. They don't really undo one another. So we have to play a trick when we want to say that they undo one another and say, well, we're only talking about the positive side of the squaring function. That is going to give us the inverse of the square root function. So we'll talk more about that when we get to the section on graphs in chapter 2. But right now we're going to be doing all the algebra things in chapter 1. Let's see now, number 16. G of x is equal to x squared minus 4. F of x is equal to square root of x plus 8. So G of x plus h is going to be an important one for you to know how to do. To f of 8. So G of x plus h is going to be x plus h squared minus 4 minus 2 times the square root of 8 plus 8. This is going to be x squared plus 2xh plus h squared from our perfect square trinomial formula. This is going to be minus 2 square roots of 16. The square root of 16 is a perfect square, so it's going to come out to be 4. So these are like terms that are going to combine. And we're done. And our inputs were x, our parameters were x plus h and 8. There we go. F of y is equal to y minus 5. G of y is equal to h minus y squared. We want to find g of f of y minus f of g of y. So we're going to do two different compositions here. G of f of y, h minus y minus 5 quantity squared. I'm plugging f in for the y in g. And now I'm going to plug g in for the y in f. I'm putting brackets around that because there's parentheses on the inside. I'm going to need to distribute this negative over the whole thing. Put brackets around this while we're at it. So we're going to have to find this squaring before we do that multiplication. 2 times 5 is 10. Plus 5 times 5 is 25. Minus h plus y squared plus 5. It's just simple multiplication there because there's no like terms, there's no squaring being done on that one. Now I need to distribute this negative over everything. This h and this minus h zero each other out. This y negative y squared and this y squared zero each other out. And we simplify down to 10y minus 20, which is a much simpler equation for us to deal with. We only have the one variable. All of our h's went away, all of our y squareds went away. So it's much easier for us to plug a value into this last form than to evaluate both of these and plug them into each other and having to square things and subtract things. And yeah, that's really messy, where this is very simple once we do the composition. So we do it generally so that we can stick in any y value that we want to, and we might want to stick in more than one y value in the end. I think I skipped number 16. Did I? No, I didn't. All right, before we leave this area, because we've been talking about compositions of functions, I want to talk to you about a very important composition of functions, which is a way that we're going to write slope of a function. And I'm going to draw a picture here. I'm going to exaggerate. I'm going to draw a curve. I'm going to estimate the slope of the curve here using 2 points. I'm going to draw a right triangle from that. So this point down here on the graph is my original input that I'm going to call x, f of x. That's an ordered pair. I'm going to call this horizontal distance here on the right triangle h, so that this point over here has an input value of x plus h, and its output is going to have to be f of x plus h. That's all that I know about the output. So another name that we're going to call this in calculus is we're going to call this delta x, and we're going to call this distance delta y, but our slope we know is delta y over delta x. It's y2 minus y1 over x2 minus x1. Let's see if we can write that slope formula given these ordered pairs that we have. So our y2 is f of x plus h minus our y1 is f of x over our x2 minus our x1, and these are going to make a 0. Get very, very, very used to seeing this formula that when we find the slope of a secant line, which is what I've drawn here, or when we want to approximate the slope of a curve at a point, or we want to find something that we're going to call average rate of change. Average rate of change is going to be a different formula, but it's the same thing. It's still y2 minus y1 over x2 minus x1. If I had called the points, if I had called these input values a and b instead, and they were given to me, average rate of change would say, okay, this is f of b minus f of a over b minus a. It's the same formula. It's still y2 minus y1 over x2 minus x1. So slope of a secant line, the difference quotient, which is what this is, and the average rate of change are all related concepts here. So what makes a difference quotient special is that we are going to use it once we get to calculus. I assume you all are in pre-calculus because you're going to be taking calculus. We're going to, in calculus, try and move this point here closer and closer and closer and closer and closer to this point by reducing h, making h go towards 0. We'll talk about this later, but this is a limit process. So we're going to make h get so close to 0 that we're not going to be able to tell the difference between 0.1 and 0.2 with our eyes anymore. Mathematically, they're going to be different by a very small amount. But they're going to be practically identical to us. And so we're going to get that estimation to be so close to the real value when we squeeze out all the air that we're going to be able to talk about what is the slope of this curve at that point right there, because we made this point get so close to that point that we can't tell the difference between the 2 points anymore. They're mathematically different, but they're not they're not significantly different from one another. So when I find the slope of the line between these 2 points, I'm basically finding the slope at that point. It's a nice little algebra trick that we play in calculus with limits. All right, well, here we are. We're going to find the difference quotients right now. That's what we just set up. So number 18, h of r is going to be 2r plus 4. So our difference quotient for this problem is going to be h of r plus, and I'm just going to use the calculus symbol here because we've already, excuse me, not h, delta r minus h of r over delta r. I'm going to set it up that way because we've already got the letter h going on as a variable name here. I don't want to get it confused. I don't want to use h for horizontal distance here. So h of r plus delta r is going to be 2r plus delta r plus 4. So there's my original with r plus delta r plugged in for the variable. Now I'm going to subtract off the original. And I'm going to divide by the change. So this is my y2. This is my y1, and I'm finding the difference between them. I'm going to divide by the change in input. One of the really important rules about the difference quotient here is that delta r, the denominator, can never be equal to 0 because it's a fraction. So we're going to be able to do something with the arithmetic here in a second because it's not going to be 0. But we wouldn't be able to make the statement wouldn't be able to do the arithmetic if that were not true. So everything that was in this original function is going to have to 0 out. You see that every term on the right over here is going to have to cancel out with something from over here. I'm only left with delta y, which is 2 delta r over delta r. And remember that delta r is not equal to 0. So because it's not 0 over 0 here, I'm allowed to say that that's 1, and that my answer that I'm going to be left with in this problem is going to be a constant value of 2. I knew that my slope was 2 on this line. It's always 2. It's right there. It's in slope-intercept form. So my answer for what my slope of the curve is matches what I know the slope of my line is. So we're going to do that again for another linear function that we know what the answer is for number 19. Just for some practice, g of y is equal to 4y minus 7. Given what we just saw, we know that the answer to this problem should be 4, but we're going to do all the work to prove it. G of y plus delta y minus g of y over delta y is going to be 4y plus delta y minus 7 minus 4y minus 7 over delta y is 4y plus 4 delta y minus 7 minus 4y plus 7 over delta y. Those make a 0. Those make a 0. Those are going to cancel because it's not 0 over 0. And that's going to give me an answer of 4, just like I knew I should have. Now, in numbers 20 and 21 that we have here, we are going to have some leftover things at the end that'll be interesting. You're going to see that, excuse me, y of x is equal to x squared plus 6, which means that my difference quotient is going to be y of x plus delta x minus y of x over delta x is going to be x plus delta x squared plus 6 minus x squared plus 6 all divided by delta x squared plus 2x delta x plus 6 minus x squared minus 6 over delta x. Let's go to 0. 2x delta x over delta x. Remember, delta x is not 0. This is going to be 2x. Oh, now isn't that interesting that this comes out and the answer to what the slope of this thing is here at any point x is dependent on what the x value is, because the slope of this curve is getting steeper as x gets bigger. So as x is smaller, as we're at 0, we have 0 slope. If we're at 1, we have a slope of 2. If we're at 2, we have a slope of 4. If we're at 3, we have a slope of 6, and so on, right? So that seems to fit with what we know about parabolas. It didn't depend at all on this y-intercept though. All right, then our last problem here for today is f of t is equal to 4t squared plus x. Now notice the x is just a letter that sits there. It's not the variable that is changing. When we find f of t plus delta t, that doesn't affect x at all. So we're going to find f of t plus delta t, because t is the variable that's the input here, minus f of t divided by delta t. X is just there to confuse us, but it's going to go away in the process, just as if it were a number. So 4 times t plus delta t squared plus x minus 4t squared plus x over delta t is going to give us 4 times t squared plus 2t delta t plus delta t squared minus 4t squared minus x over t. So this is going to be 4t squared plus 8t delta t plus 4 delta t squared minus 4t squared minus x over plus x there. Delta t, this plus x and this minus x make a 0. It's minus 4t squared and that 4t squared make a 0. Everything that's left has a delta t in it, so I'm going to divide by delta t. This is going to be 8t delta t over delta t plus 4 delta t squared over delta t is going to give me, it's going to be one of those left. It's going to be none of these left. Give me 8t plus 4 delta t. So this one depends not only on what the input is, but how far away from that input my second point is. I want to check and make sure that I didn't make a mistake in number 20 before we leave, because I think I should have ended up with a delta x term in it. I'm going to go back and do number 20 again really quickly. That this is x plus, let's call it h squared plus 6 minus x squared minus 6 over h squared plus 2xh plus h squared plus 6 minus x squared minus 6 over h. Yes, I made a mistake in the next to last problem that I should have ended up with 2 terms and I forgot to write this term down. This would be 2x plus h. And I said it was just 2x. It's my fault, I'm sorry. Or 2x plus delta x. So when you have parabolas like this down here, whether they're parabolas in terms of x or t, you should end up with part of it is determined by what the value, what the input value is, and the other is how far away was the second point to determine the slope, because it's not a constant ratio between points like in a line. So, okay. Thank you for your time today. Let me know if you have any questions. Have a good day.